Hello. That's week 10. I guess time flies. Welcome to last week of our course. So everything up until week 9 is they can be put in an exam, and in week 10 on Monday we're going to talk briefly about the history of database as well as modern databases. So this part of the course is not going to be heavily tested in exam, and I'll give you exact idea like what you're expected to know if we do ask a question from this part of the course. So a couple of things to announce. I think the due date for assignment 2 is tomorrow. So please submit early. And in the last assignment, we got many people emailing us. They cannot access the server in the last minute because obviously too many people are trying to access it, and then they couldn't submit it on time. And if you submit like 1 minute, 2 minutes late because of the server, we don't like. I will not take points off you, but just be mindful to plan ahead. And you can actually submit multiple versions, and we will grade the latest version up until the deadline. Okay, and what else do I have to talk about? Okay. Also the My Experience surveys opening up, so that's a great way for us to know, get some feedbacks from students so that we can continue improving our course in the future offerings. So we do appreciate any feedback from you. Okay, so today we're going to talk about basically we're going to, in the first half of the lecture, we're going to talk about NoSQL databases, which is basically the fancier version of relational database. And the part 2, we're going to talk something more recent, which is the vector database, which is the backbone of everything you're playing with, especially in for large language models. So everything if you're interacting with large language models, then most likely you're playing with a vector database. So relational database dates back to like 1960s, and in 1975, IBM they were trying to organize their files, and then they proposed the first relational model. And after that, we got like 50, 60 years of development for relational database. So relational database is still super relevant. So let me see if I can, I think I got a DB engine ranking. So up until April 2026, you can see that the top 10, you can see all of the most popular highly ranked databases in the world, and among top 10, at least 6 of them are still relational models. So relational database is a huge part of the database, and when you go to a database conference, when they talk about a database, most likely they're talking about a relational database. And if they ever talk about other database, they will specify what kind of database they're talking about. So what happened to the relational database? What happened to the relational model? Why did people need to change it? Well, it all happened in the kind of around the time in .com bubble, and also especially in the big data era. At first, Google was trying to index the whole internet so that it can build a great search engine so that you can search anything on the internet. So what they're doing is that they're literally trying to index the whole internet. And when you're trying to do something at that scale, the relational data model kind of breaks, because if you think about it, the relational database is great for transactions. So we talked a lot about reading and writing and the transactions and modifying the database. So the relational database is best suited for online transactional processing, so OLTP, which is great for like banks, which is great for your college application, anything that requires a lot of read and a lot of write, and you need to make sure that you need to get the answers 100% correct. And after that, people started to, they want to scale up their business, and they have a huge amount of data, especially in the big data area. And they have more data that they can process. So what ended up happening is that they're not really concerned with modifying or writing to their database. They're more interested in grabbing a dump of data, analyze it, analyze customer behavior, and then they can change their application. So that is a slightly different, that's a completely different process from online transactional processing. So that's called online analytical processing. So basically, so that's when those job titles like data engineers, data scientists, and data analysts came up. And the great thing about that era is that we don't care too much about modifying and writing to the database anymore. We care about analyzing the data a lot more than modifying the database. So if you stick to the traditional RDBMS, because we have a well-defined schema, it is designed for transactional processing, it's going to be a very rigid schema. So for instance, if you have a table and then your client says, now our product has one additional column, what you end up doing is that you need to go back to talk to your boss, and you start from scratch, and then you need to revisit your whole ER diagram, and then you have to translate that into SQL, and then you need to check whether the constraints are still holding. And you need to change all of the triggers. You need to change a lot of stuff just to add one column. And a lot of times, we don't need a robust relational data model anymore. So what happened is that, just like we mentioned in the first lecture of the course, they started to relax a lot of the constraints that we have been imposing on relational databases. So we have been talking for 9 weeks about the constraints and what we should do and should not do. And then in NoSQL databases, they're slightly changing those constraints, they're slightly relaxing those constraints to accommodate the big data area. And so here is a comparison between SQL versus NoSQL. And NoSQL databases, they are mostly non-relational. And what you need to, the takeaway message is that NoSQL does not mean it is like a complete different database and it's like getting rid of SQL forever. NoSQL means not only SQL. So basically, you can consider them as a niche database, and you consider them as a extension to the traditional relational database. So all of these NoSQL databases, we're going to talk about the key value pair database, the graph database, which is my specialization, and document database, as well as column-based databases. They use a very similar query language. The query language is still declarative. If you know SQL, it is super easy for you to migrate to that database, and that is the intended. That is intended. So they are built so that existing relational database users, like PostgreSQL users, they can easily use those other databases like document, graph databases, key value pair databases, and column databases. And for relational databases, we have strict ACID style guarantees. So ACID, the 4 properties, atomicity, consistency, isolation, durability. We talk about these 4 letters for 9 weeks, and these 4 properties are intended for transactions to go through correctly. Well, in NoSQL databases, we don't care too much about ACID, It's more about the volume and speed and flexibility. And another thing we talked about, so another angle we can look at the NoSQL database is that when we talk about normalization theory, we're always looking at the redundancy in data, remember? So I'm kind of giving a revision as well. So we're trying to identify the redundancy in databases by using functional dependency, and then to get rid of that functional dependency related redundancy, we proposed all kinds of normal forms, and the most important ones are third normal form and the Boyce Codd normal form. And after we go through all those algorithms, we end up with smaller tables, and then that in theory eliminates or at least reduces the redundancies we have. And the reason why we want to remove redundancy is because we talk about 3 types of anomalies: update anomalies, insert anomalies, delete anomalies. But if we think about it, if we don't do update very often, and if we don't delete every often, and all we do is read, then redundancy can actually be helpful, right? Because you have like different copies of the data, some distributed around the world, and it's a lot safer than storing it in a central server. And that kind of idea is applied everywhere in the tech world. And if you look at blockchain, if you look at cryptocurrency, everything has been more decentralized so that it is faster and it is essentially more secure in its own way. And so basically, and bring it back to NoSQL, redundancy makes everything faster, and sometimes it makes it even more reliable. Because when you have one copy of the data sitting in the central server, if that computer is gone, then your database is gone. But if you have like different replicas of the databases of different versions distributed around the world, like you have one copy in Saudi Arabia, you have one copy in China, you have another copy in San Francisco, and then they have the history, they all have the version history of the same database, then it's a lot harder for your database to go down. So you're looking at much more uptime as well. And in NoSQL databases, like I don't really like their categorization because there are other NoSQL databases that don't fit under these categories. But for the purpose of this course, we're just going to talk about them in this order. So we got a key value databases, which is the idea behind it is that a lot of times we need fast read, and we need to match something very fast, and the great way to do that is using the hash table. So you can consider key value database as a giant hash table, and we also talk about document database. So document database is kind of like a self-describing database where you can keep padding on the attributes. And the way we think about it is we think about the JSON file. So in a JSON file, every instance of the every instance of in a JSON file, they don't always have the same attributes. So one JSON can have all, for instance, 100 attributes, and then the other JSON object can only have 5 attributes, and that's a much more flexible way of storing data. And for wide column databases, so again, in practice, we're dealing with giant amount of data, and then the number of columns can get very, very large, like thousands or tens of thousands columns. And at some point, the number of columns is like even closer to the number of rows. And in that sense, your whole table is like very sparse. And we need a special technology, special techniques to handle those sparse rows. So a lot of the rows, they only have like a few attributes with not null values. And for graphs, that's my specialty. So when it comes to modeling the relationships between objects and entities, it is best to model them as graph data. And there are a couple of ways to store graph data, and then we wrap them up into different types of query languages. And for key value pair database, we are just talking about, you can think about it as a giant hash table, right? And hash table allows constant time lookup. And do you remember the two types of indexes we built in PostgreSQL? There are two types of indexes that, so can anybody tell me what are the two types of indexes? So what is the most important type of index? B-tree, right, great, I'm so glad I hear that. So, and B-tree is the one that we built for primary key, and the other type of index is that we can use a hash map, we can use a hash to build an index. And why do we need to build an index? The reason why I build an index is that we want to store some intermediate results, or at least we want to store the roadmap for finding those rows. And what is the advantage of a hash table? A hash table is fast for exact matches, but is not so great for what kind of query that B-tree is great for. So a hash table is great for exact matches, but it's terrible at range queries, right? Because you cannot, because the values are not sorted in the hash table, so it's terrible for a range query, and it's terrible if you want things to be sorted. So, so that's where that's going to carry on to the key value pair database. So when we design a key value pair database, we're expecting the query to. We won't expect a lot of range queries for key value pairs. Okay, so this is like nice visualization of the sizes of these NoSQL databases and the complexity, and the key value pair database incurs the most size because they need to build a hash table for every column. And then we got column families, and then we got document databases. And the graph database actually is the smallest, but it is the most complex. So, so this is the screenshot I was looking at. So we talked about this before. And another important type of database, which does not usually fit into NoSQL, is the distributed database. So a distributed database is mainly to improve the reliability of your traditional one-server database, and also it makes query a lot faster. So there's a specific track dedicated to distributed database. So the idea behind distributed database is that instead of scaling a database vertically, we want to scale them horizontally so that it's much cheaper. So it's like if you have one employee, you can give him $10,000, you can give him $1 million, but at some point, his productivity is not going to increase that much. But instead of giving $1 million or $10 million to one employee, unless he's really, really great, you can give like $10 million to 100 employees, and then they can do these things simultaneously, and then they can give the results back to you. And that's the idea behind distributed database. So instead of scaling the database vertically, so instead of making this one server a supercomputer, we just pad on some cheap commercial servers which host these databases, and then they work together, and then they communicate with each other, they talk to each other to answer your question. So if you, and the data is stored in different data servers, and then each server has a replica, has a replica of certain piece of data. So basically each piece of data is stored redundantly and distributedly in different servers, so that if one server goes down, most likely your data is still fetchable from another server. And when you ask a question, I think The classic example of distributed database is the example of MapReduce. I think most people have heard of MapReduce. So if you want to count number of sentences or number of words in a sentence or number of words in a document, what you end up doing is that you chop that into smaller pieces, send them to different distributed databases. Each one of them will count a number of words for you, and then they will aggregate and send it back to you. And beyond that, we have, so that's MapReduce, and beyond that, we had Spark, and after that, I think people are still using Spark. So if you were interested in distributed database and other NoSQL databases, especially distributed database, I think we have a course called Big Data, which is COMP3311, and you'll learn all about MapReduce, Spark, and all that distributed database. Okay, so so basically the idea is that we partition the database into different splits, and then we're storing them redundantly so that we can have the best balance between consistency, accuracy, and accuracy. Okay. So key value pair database. So for key value pair database, the idea is that we consider this as a giant hash table, and we need to first partition the data, and then we need to hash them into different keys, and then this allows us to fetch those records super fast. And as we have discussed, this is great for exact match, but it's not so great for range queries. And so these are some examples, like if you're trying to store the session, if you're trying to fetch related to a very long string, like a session ID or something like that, like a URL or your timestamp, that's a great way to use. That's a great time to use key value database. And the good fit is that we have the keyed path, hit rates, and catch coordination. And what is not so good is when we want to do a lot of joins on the tables, and because if you only build hash tables, it's very hard for you to perform joins, because usually we need a B tree to make the join a lot more efficient, and so it's not so great for joins. And document database compared to traditional database, document database is like has a self-describing schema, in the sense that it doesn't really have a fixed schema. As long as you keep padding, as long as you're describing the attribute in the JSON file, then you have a new attribute. So it's very easy for us to add new attributes in a document database. In the traditional relational database, because everything is stored in the table, in the table, if you want to add an attribute, add a few attributes, you need to add a whole column in that table, and then a lot of the values could be no values. And so for document DB, you can think about it as a JSON file, and it is best fitted for semi-structured records, like maybe like in today's world, like the markdown files and experiment logs and system logs. Like in the system, we have a lot of logs, and it is best suited for things like that, and is not. And if your data is like super structured, then you should just go back to the traditional relational database, because relational databases are designed for structured data, and for semi-structured records like logs and anything that's JSON shaped, or even just a decision tree or something like that, you're better off with a document database. And also we can also store the in the time of big data, we can also store the data differently. So traditional relational databases are stored in a column, in a row-oriented storage manner, in the sense that adjacent rows are stored adjacently on disk. And the bad thing about that is that if you're only fetching a couple of columns from disk, then if you have like 1 billion or 10 billion rows, then it takes a long time to fetch all those records and only look at maybe 2 attributes. So imagine you have like 100 attributes, and then each row has 100 attributes, it's stored in disk, and you only look at 2 attributes. Then you need to grab all those rows and then map to or project to, as we say in relational algebra, to that 2 specific attributes that you're interested in, and then you need to process all of them. And to tackle this in the big data area, what they come up with that is they store the data in a column-oriented way, in the sense that each column's values are stored together. So they don't consider, so when they don't consider rows when they are storing the data, they're considering the columns when they're storing the data. So basically, each column is stored in the one place, and each column is stored in one place. And if you're just fetching, so for instance, if you have like 100 columns, and we are only fetching maybe the name and the salary, then we can just go to those 2 places and then fetch those 2 columns, and without touching any of the other data. So that's the motivation behind column-oriented storage. And based on that, we also have we can also design the wide column NoSQL database. So wide column NoSQL database is basically where we have this technology to store these sparse rows. So when you have when we have a very wide column, say 1,000 columns, and when you only have let's say to have for an extreme example, if you have 300 rows and 1,000 columns, then a lot of those columns, the values will be null values, because if you've been working with machine learning and if you're working with deep learning, you know that if you have too many columns, if you have too many features, it's very hard for us to extract anything meaningful from those columns. And also it's a waste of space, and because the table end up with a lot of holes, which is not something we want. And so wide column database, for each row, they only store certain columns, and also they're indexing it in a way such that it is still easy for us to just grab each column from the database instead of looking at each row. And lastly, we have the graph data. So graph is basically you can consider it as a data structure, or you can consider it as a data model that we have all learned in discrete math. So what are the 2 classic ways to store graph data? So graph is basically a collection of vertices and edges, and it's great for modeling the relationships between entities. So we can have, in a social network, every person is a node, and every person is people. Every connection represents a mutual friendship, and also we can have a directed edge to capture the following relationship on Instagram. If I follow you, that's going to be an edge from me to you. If you follow me, there's an edge from you to me. And so that's kind of a very useful data model in discrete math, and something that you should have learned in data structures and algorithms as well. So can anybody tell me what are the most popular, or what are the 2 fundamental ways to store graph data? So how do we store graph data usually in a computer? Pardon? Adjacency matrix. That's great. That's very great. What is the other one? Adjacency lists. So you mean edge list. So adjacency list. Great. So I'm so glad you guys mentioned them. And let's just say that the number of vertices is like n, and a number of edges is like m. So what is the storage cost if you're using a adjacency matrix? N squared, exactly. And for adjacency list, m, right? Yeah. So that's very good. That's very good. I'm impressed. So basically, if you're trying to store all this data, like you have like billions of users and their connections, in machine learning, what they want to do is that they like to store graph as adjacency matrix because they can do all kinds of fancy stuff with the matrix. But if the graph if the number of vertices is exploding like billions of users, then what we really do is that we store them as adjacency list. So adjacency matrix, it takes the space of big O n squared because we got n vertices and as rows and columns, and for each pair of the users, we need to mark whether they know each other or not. So that's like n squared storage space complexity. And if on the flip side, on large-scale graph data, what we usually do is that we store the adjacency list or the edge list. So basically, for every connection that we have in the database, like I know you, you know me, I know him, and we just write that down in the edge list, or we write it down in the adjacency list, and then in the end, the storage cost is just the number of edges. And the number of edges in practice, it is usually much smaller than n squared because most graphs are sparse, and most graphs and most degrees, they follow the parallel distribution. So we have a lot of low degree vertices, and we have very few high degree vertices. So, so that's great. You know the basics of storing data. And when is graph model used? It's mostly used when we have a multi-hop questions. So I remember we had like a final exam question in previous offerings of 3311 where we were using a relational model. We were using a relational database to store the relationship between people. So basically, we have a giant lookup table that stores who knows whom in that table. And then the one of the final exam question is that like if I know you, that's one hop, and then you know somebody else, that's a two hop. So the final exam question is like, can you list me all of the 6 hop neighbors of you based on this data set? And it was a super complicated query to do in SQL, in SQL, because PostgreSQL is not intended for things like that. That's why it's so hard. And for graph databases, and if you just switch from PostgreSQL to graph database to a real graph database, then that question is going to be a lot easier to answer. So basically, when we want to answer any question about multi-hop traversal questions on for related to relationships, then we need to use graphs, and because it is the most natural structure to store the relationships between different entities. And so they have this idea called property graph. So all of the so if you think about the ER model that we had, so the ER model is kind of like a graph. So we have the entities and we have the relationships, and on top of that we also have attributes. And in the entity, in the property graph, basically we're getting rid of the attributes and we're left with the entities and relationships. And entities and relationships are basically mapped to vertices and edges. So if you ever encounter into an ER diagram that is so complicated that you feel like this looks more like a graph, then maybe that's the sign of moving to a graph database. And let's see. And we also have the okay. And we also have a language for graph database. So Neo4j is the best known property graph product, and we also have the Cypher query language. So you don't have to understand or use any of these. And just to know that we have devised different languages, different SQL languages for different NoSQL databases. Okay, I think it's a great time for us to go through a couple of quizzes so that you have a basic understanding of NoSQL. So as I've mentioned, obviously I don't expect you to become an expert in NoSQL, but these are the things that so these are the basics that we need to know. So first, what does NoSQL stand for? What does NoSQL stand for? Non-operational, non-open source, or not structured SQL? So what does it stand for? B, right. No, so it stands for not only SQL, so that's very important. So the name is like, it's kind of confusing when people think about NoSQL. They thought we're getting rid of SQL at some point, but we're not. So which of this is not one of the 4 NoSQL families? So the NoSQL families are the key value database, document database, graph database, and one more. So definitely not a spreadsheet. So we talked about, so distributed database is not one of the 4 NoSQL families. So we got the key value, and we got wide column, and we got graph database, and we got a document database. And and the third question, a key value store, or you can say a key value database works like a dictionary. What is it not good at? So we know that is definitely good at fast lookup by key. So that's the whole point of key value database. And is it good at catching frequently accessed data? Yeah, because most likely we can build a hash table around it. And is it good at storing session data? That's one of the examples. So it's great at storing session data, catching frequently accessed data. And what it's not good at is not really good at finding the records that's sharing a common property. And in the document database, let me see. So in a document database, what kind of format do they usually use? So I think 2 of them we just throw in there to mess with you. So definitely not Excel spreadsheet, and definitely not PDF files. So do we use JSON or do we use plain text? JSON. So JSON is the backbone of document database, and I think every programmer has used JSON at some point, and now it's great for is used a lot for like configuration files and like storing data in general. And number 5, different records in a document database can have different fields. So what is this called? So this is a flexible schema, and this is a better way of saying is this is a query based schema design. So in the traditional database, what we do is that we have a fixed schema, and then we have the data, and then we have to write queries to work around those data. And in NoSQL database, what usually happens is that they look at the queries first, and then they use the query to design the schema. Okay. Wide column databases store rows and columns. Why they're not so what is the difference from the relational database? So A, they don't support the same kind of query language. B, different rows can have completely different columns, and they're designed to scale across different machines. C, they only store numbers, not text. And D, they don't have the concept of table. So a lot of these are common misconceptions about NoSQL that you should avoid. And if you don't know the answer, just pick the longest one. So basically, B is the answer. So different rows, they can have completely different columns, and that's the point of a wide column database. So we could have like 1,000 columns, and I can have meaningful information in 10 columns, and you can have meaningful values in another completely different 10 columns. But we all share this 1,000 column schema, and it's a lot easier to add or remove a column in this way. So in the graph database, what does an edge usually represent? So edge, does it represent a type of index, or does it represent a column in the table, or does it require something about the database server? So usually in the graph database, an edge represents the relationship between two nodes, and a node usually represents an entity. So basically, an entity is anything that is kind of like anything that can be modeled into, so anything that's a noun is an entity, and a node is usually representing an entity, and the edges are usually representing the relationships between entities. So, all right. Which NoSQL database would you most naturally use, so most suitable for a model or social network where you need to get friends of friends? So if you go on to YouTube, Facebook, if you go on to Instagram, a lot of times they say, here is somebody you may know, and here is somebody you probably know. So that kind of recommendation is based on what type of NoSQL database. Is it based on key value database, document, wide column, or graph database? Graph database, exactly. So social network is the giveaway. So social network is basically a graph, and if you want to find friends of friends, you need to model these relationships into a graph. So social network is the best application, is probably the most fundamental application of graph database. And so when we talk about SQL databases scale up, so how do most NoSQL databases prefer to scale? So SQL databases, we usually scale it up, so we make this server super great. We tune the parameters in the PostgreSQL config file. We build indexes, we build this and that, and we optimize the server to make it scale up, to make this one server a super server. And how do we scale NoSQL databases? Like, what is the idea behind NoSQL database? So do we so don't scale? Do they scale at all? No. Do they scale at all? So NoSQL database is like definitely is specifically designed for large scale of data, and then the main idea, the main motivation is that we can throw in a lot of cheap commercial servers to store data redundantly, so that we can have higher uptime and we can handle queries much efficiently. So you can say, you can say they scale sideways, and data is duplicated on identical machines. Well, I guess the better word here is they scale horizontally. So instead of vertically, they scale horizontally because we throw a lot of cheap commercial servers to help with the original server. Okay, the last one. So which one describes the difference between SQL and NoSQL databases? So SQL databases are newer, faster. NoSQL databases can never handle structured data. And SQL databases use fixed schemas, great for structured data. NoSQL database offer more flexibility and scale for varied workloads. NoSQL database always replace SQL in modern systems. So I guess this is, so the answer is C. So whenever you see a multiple choice question, a choice is is speaking in absolute terms, then most likely is wrong. So if you're saying that NoSQL databases can never handle structured data, that's completely wrong. So NoSQL databases are a great extension to the existing relational databases, and they can definitely handle structured data, and they're just built for semi-structured data and non-structured data. So C is the correct one. So SQL databases, they use fixed schema. They're better for structured data, and NoSQL databases, they have a flexible schema, and they're more suitable for semi-structured data. Okay, let's take a break for 10 minutes, and after the break, we're going to talk about a very new database called vector database and how it's going to be beneficial to almost all of your large language model applications. right, so let's go back to our lecture. So we talked about NoSQL database, and most of these databases are introduced in the big data era, and some people they come to me after lecture. Whenever I deliver a NoSQL lecture, they come to me and ask me, is it still worth learning PostgreSQL? And the good news is, as you have seen, the PostgreSQL is still ranked, it's among the top ranked databases out there. And the reason why it can do that is because they're constantly improving PostgreSQL to match the functionalities these NoSQL databases can do. And I'll give you another example at the end of our vector database discussion. So let's talk about another more recent database, vector database that cannot really be categorized as either relational or NoSQL. So recently, especially in the last 4 years, the rise of large language model has changed our lives forever and introduced new challenges as well as opportunities for database research. And two types of ways when database people like me look at large language model is that how can we use large language model to improve our database? And on the flip side, how can we use database to improve large language models? Well, there's one thing that we can do to use large language models to improve database is they have something called text to SQL. So basically, you have this nice system built for you where you can basically use natural language to interact with relational database. And the reason why I didn't talk about that in the start of the course is because if you all do that, then there's no point of doing the assignments. So I saved to the last to talk about, maybe you already know how to do that. Maybe you already know the existence of text to SQL system, but that's fine. And today we're going to talk about the flip side. How do we use database to improve large language models? That's like a very interesting new era and a new field that's like super important because a lot of these previous NoSQL databases they're most relevant for these tech companies and they're most relevant for maybe software engineers, data scientists, data engineers, for people with those job titles. But if we can actually use database to improve large language models, it will change the lives of everyone, and it has already done so. And how do we do it? Well, the point of large language model is that initially, Sam Altman, they have done this for many, many years, actually. They have tried GPT. They have tried, before 2022, they were training different types of small language models. And after that, they had enough data to train their first GPT model that is available for us to use. And at that point, it was a shock because everyone didn't expect AI to be so equivalent, to be so well spoken, to be so knowledgeable. And what they actually done is that they're kind of storing all of the knowledge, human knowledge available on the internet into their parameters. So that is what they've done. They have built a very great general purpose model that is great at finishing your sentence. So that's it. They're great at finishing your sentence, but a lot of times after we're past that impressed stage, we realize that large language model, they make a lot of mistakes, like more mistakes than you can imagine. Like I think all of you can attest to this. They make up stories, they make up facts, and they have a specific word for it, and they have a very fancy word for making mistakes from large language model. They call it hallucination, as if it can really think. So basically, they made mistakes, and they call it hallucination. And why do they make mistakes? Well, they don't really have any data sources. They don't really have the ground truth data to look at. Because as humans, if you ask me a question, if I don't know, I'll just say, I'm sorry, I don't know. I will just look it up, and I'll go back to you. But large language models, they have this tendency to please people. They have the tendency to make you happy, and they always pretend they have the answers. So what they end up doing is that they're obsessed with finishing your sentence, is that they make up a lot of fake data, and they make a lot of fake news. So when I'm writing an academic paper, I ask it to provide me with references. It provides me with fake references. I ask about current events, and it's capped at, for instance, right now it's 2026. If I ask a question related to 2026, maybe about the Strait of Hormuz, anything like that, an old model that is not plugged into any database, it will say, you know, the oil price is fine, and the cost of living is fine, and the stock market is fine. Why is that happening? It's because every large language model has they can only answer questions up to a specific date. Like for ChatGPT, at some point, it can only ask questions up until 2022 October. And if you ask questions about 2023, it will say it doesn't. It will say it did not happen. So at some point, we're tired of that, and everyone wanted to improve their quality of answering. And this is not only relevant to us interacting with generative AIs on the browser. It is also super important for software engineers, data scientists, and all people with tech jobs to have reliable answers from large language model. Because now large language model has been already applied to all fields, especially in the coding field. They're using coding agents to write code for them. And how do they make sure what they write is, how do they make sure that large language model gives you the better quality answer? I'm not going to say 100% correct answer, but how do we make sure that their replies have higher quality? Well, as database people, we naturally want to plug a database to the large language model so that when it answers a question, first it knows it will always look at the database and to get the real answers, and then they will grab that answer to phrase it into a couple of beautiful sentences, and then they will reply to you. So that is the gist of retrieval augmented generation. So RAG, this is a retrieval augmented generation. This is the most important, this is the direct application of vector database. And this is the reason why vector database is so popular. Vector database has been there for a while, but people don't really pay attention to it. But now, recently, vector database is exploding, is because it can help large language models. So basically, large language models are responsible for the generation part of RAG, and then databases are responsible for the retrieval part of RAG. So basically, vector database is responsible for retrieving the correct answer, and then we pat that, give it a prompt to large language model. It will then give you a good answer. And the thing is that how do we know what is best for this question? Well, that is exactly where we need to talk about vector database. So vector database are best for capturing the semantics of human language. So when we're looking at traditional relational databases, we need to predefine a bunch of fields. We need to define maybe a couple of fields, and then if we want to have nearest neighborhood matching, we need to go through all those fields, right? For instance, if you have like students' data, you have their height, you have their or maybe athletes data. You have a table about athletes. You want to know who is the best athlete in this table. You need to query all those columns. But in vector database, the text information, the text data, is stored as vectors. So we have a huge, if we are given a huge document, what we do is that we split it into different chunks, and every chunk is mapped into a vector in the vector database in a way that we can do semantic matching. So in PostgreSQL, when we want to match a string, we need to use inbuilt pattern matching, or we need to use regular expressions. And but in vector databases, because all of the texts are embedded into vectors, we can the problem reduces to finding the nearest vector in that space. So instead of doing exact matching and keyword search, we can say something like we need to search for where name is related to the United States of America, or where the person's name has animal's name in it, or the person's name has is similar to Jerry. And that opens up a lot of opportunity, because it is a much more powerful query. So what is an embedding? Well, if you're taking AI course in UNSW, if you've taken 9417 or Introduction to Machine Learning, you should know that embedding is just a bunch of numbers. Embedding is a vector, and the reason why we call it embedding, they like to invent fancy words. The reason why we call it embedding is because when we're looking at unstructured data, we want to map it, we want to embed it into a structured space. So if we want to embed it, if we want to map it into a 100-dimension space, then if we can map it like that, then the unstructured data becomes structured data. So if you have like the Harry Potter book, or you have like COMP3311 syllabus, that's unstructured data. Like, I don't know where to start. I don't know. The computer doesn't understand what it means. But if you map it into a bunch of vectors, each vector has a fixed length, say 1,000 numbers, then it becomes structured data, and that can fit into the table. And that's why it's called an embedding, because we're kind of embedding the data into the vector space. So when you say embedding, you know that it's just a fancy name for vectors. So now we can represent things in vectors, and then what? Well, the great thing, the way we map these things into vectors is that we want to ensure that they have this property. So we want to make sure that if two documents are semantically close and they're semantically similar, then their vectors needs to be spatially close or spatially similar in the vector space. So let's just say that we have dog and cat, right? Dog and cat are both animals, they're cute, we love them, and semantically, they're pretty close. They're closer to each other than they are to, say, lions. And if we map these three animals into a vector space, or we compute the embedding of them, then if you compute the cosine similarity between cat and dog, then the similarity is going to be very high. And if you compute a cosine similarity between the lion and the dog, or the lion and the cat, is going to be much larger. The similarity will be much lower than the similarity between cat and dog. So basically, they have designed a way, so we have like 10 decades of research behind this. They've designed a way to map sentences or words into vectors such that the vectors cosine similarity capture the semantic similarity in the original document. And that is what we can take advantage of, Because remember our original question, what do we want to solve? We want to improve the quality of large language models. And when it comes to improving large language models, what have we learned? We know that we can't really change large language models' internal parameter because that's Sam Altman's job. That's Elon Musk's job. That's not my job. Our job is that we need to provide it with the right context. So for large language models, context engineering is everything. And for database people, we are best at providing context to the clients. And in this case, our client is a large language model. So what we need to do is that we need to provide the right context to the large language model so that it can know what piece of the document is most relevant to the question. So if you ask a question, hey, I'm reading a Harry Potter book, and who is Harry Potter's best friend? And if you just ask a question like that to GPT-2, GPT-3, sometimes it will get it wrong. Sometimes it will get it right because it is embedded somewhere on the internet generate general knowledge. If you ask it a more niche question like, how did Harry Potter meet his first friend? Then it will actually need to read the vector database that we built from the whole Harry Potter book, and then it will compute the cosine similarity between that question and each chunk of the book. So the book is chopped up into like thousands of chunks, and then each chunk is a candidate for the context, and we need to find out the chunk that is the most relevant to the question. So the question is, who is Harry Potter's best friend, and how did he meet his best friend? And we need to compute these pairwise similarities, and then we need to fetch. What you usually do is that they fetch the top 10 or top 100 chunks that are relevant to your question, and then they feed these chunks to large language model and say, hey, here are the chunks that I have found most relevant to the question. Please use these chunks to better answer your question. So that is context engineering, and that will make large language model focus on the right part of the book. And how do we do it though? Well, this is if you have learned information retrieval, if you've done algorithms, know that this is basically a nearest neighbor query, right? Each chunk of the document is like one point in the high dimensional space, and then your query is going to be another point, and then you need to find your query point. We need to find the closest chunks around your query. So that is a nearest neighbor query. And how do we compute the nearest neighbor? Well, we need to compare your query node with all chunks. And if you have like 10 million chunks, we need to compute 10 million cosine similarities. And that's going to be a lot of comparisons. And also, each vector has like about at least 700 dimensions. So that's a lot of computation if we're using the brute force. So basically, what happened is that just like a lot of engineering problems, the naive approach gives you the best result. However, it is too slow. So as engineers, we settle for something that works. So that's why we need to do approximate nearest neighborhood. So basically, we need to strike a balance between effectiveness and efficiency, and we can forget about fetching the most relevant document. We can just fetch approximately the best document and in an efficient manner. So ANN is the way to go. And so brute force is too slow, no index. We need to compare our query vector with every other vector, and it's only good for small data sets. So if you got like, for instance, your essay, you need to submit to one of your humanities course, or if you got your assignment, something like that, then probably you can get away with using brute force to find the most relevant chunk of your document to your question. So that's our goal. But if you got anything that's huge, like the whole internet, or what else is huge? Well, all of the Harry Potter series. Like if you got something like that, then exact match doesn't work anymore because it's just too big and it will take forever to grab the 100% nearest neighbor of your query. So what will end up happening is that we could have two algorithms. They're both widely used. We can use the inverted file index, or we can use the hierarchical navigational small world. So they're very interesting concepts, and especially the HNSW approach is fairly new and is used tremendously. And you guys are probably using it without realizing it. So let's first talk about the inverted file index way. So for inverted file index, so basically what we could do is that we could run a K-means algorithm. So if you have taken data mining or machine learning, you know that there's a way for us to group a bunch of vectors into clusters. So it's kind of like grouping cities according to a country. So we got a bunch of cities over here, let's call it China. Here got a bunch of cities over here, let's call it Australia, and then let's got a couple of cities over in Europe. We call it maybe we'll call it Germany. And basically we got different clusters of vectors, and each cluster, for each vector, we ask it to remember which cluster it belongs to. And then, so this is pretty straightforward. And then when you ask a question, right, then it will fall into one of these clusters. And then we only search the relevant clusters. So it's kind of like we have information about China, Australia, and Germany. And if you ask me a question about Australia, I'm not going to bother comparing your question with any data points in Germany or in China because I already know that you fall under this scope. So I'm only going to compare your vector with the vectors in Australia. So that's going to speed up your process by at least k times, and that is good for medium data sets. And for huge data sets, we need something more fancier that relies on graph-based index and multi-layers, and as the industry standard for high-performance open search. So let me ask you a question, so that I can know whether you have used it or not. So has anybody used Claude Code or OpenClaw? I feel like OpenClaw is pretty popular in the last few months. And so if you have, but anybody used Cursor or any coding agent? Or so if you, oh, I guess you don't want to tell me, because if you tell me, then I may check whether your assignment is generated by Cursor or anything. Maybe we should have that conversation after the course. But anyways, if you use any kind of coding agent like that, if you're using OpenClaw, which is open source, if you're using Claude Code, if you're using Cursor, they have something called a memory. So what memory does is that it memorizes your preferences and it memorizes the structure of your project, so that when you ask it a question, hey, modify this, hey, change my SQL queries so that it passes the auto test. If you ask it any question like that, it needs to understand what part of the file are you talking about. So how does it do that? It has a vector database as its memory. So basically, the vector database acts as the memory part, as the memory component of these coding agents, and then it memorizes what you're talking about. So when you open up Cursor, when you open up things like that, sometimes it asks you, hey, do you want me to index the whole code base? Do you want me to index the whole project? And most likely you want to index that, because that's when it is indexing your code base, it is actually cutting your project into pieces, and it creates embeddings for each chunk of your code, and it stores into a nice vector database, and that vector database usually is a SQLite database. So I think you guys have already been exposed to SQLite database. So it's a super lightweight database, not as complicated as PostgreSQL. And usually they use a SQLite database to act as the memory of these coding agents. And how do they fetch the relevant chunks if they don't use the brute force, if they don't use inverted file index? They're actually using hierarchical navigational small world. So what they're doing is that the motivation behind this technique is that it kind of borrows the k-means and clustering approaches. So let me go to so basically it breaks these vectors into different layers, and the first layer is the most coarse layer, and the second layer is the less coarse layer, and the third layer are the real vectors. So basically, first, the red point is your input query, and what we need to do is we need to find the nearest maybe 10 blue circles around you, but if we have like 1,000 dimensions, it's very hard to do that because we need to compare it with all these little dots. So what ended up happening is that we provide a rough map of these vectors. So here, each blue dot here represents a cluster. So this one represents a cluster here. This one represents a cluster here. These two represents two clusters in this here. And what we do is that we slightly narrow down our search scope as we go down a layer. So initially, we're searching for our nearest neighbor around this cluster ID. So basically, we're looking at these clusters, and we say, which cluster is closest to me? It turns out that this cluster is closest to me, and then I move down to one layer. And then in this layer, each dot is still representing the clusters in the next layer. So basically, each layer is representing a cluster ID of the next layer. And in here, we're trying to find the dots that are closest to me. So this is slightly more fine-grained than the first layer, and then we may need to find we may be able to find like 3 of them. And then we pick the one with the shortest distance, and then we go from there, and then we just go from there, and then we search around that area. So it's kind of like a multi-level highway system where if you want to get to where I live, like right now, for instance, I live in Kingsford, and if you're an alien, and if you're an alien, and if you want to get to my house on Earth, and first of all, you need to look at the whole world as a bunch of continents, and then my location is abstracted to maybe Australia, and then all the other points, all the other locations, they're abstracted to Europe, Asia, Africa, South America, United States, North America. All the other continents. And the alien will look at these continents and they will say, Jerry lives in the continent where Oceania continent, so Australia. It will go to this continent, and then it will look at all the countries in this continent, and it will discover that my location is closest to the cluster ID of Australia, and then it will go down one level, and then it will look at all of the clusters in Australia, basically the states in Australia, it will discover that my point is closest to New South Wales, and then it will look at all cities in New South Wales, and then it will see that I'm closest to Sydney, and then it will, in the end, it will discover I am in Kingsford. So if we look at the flat index approach, that would mean we need to take every address on the whole planet and compute the cosine similarity with my address. So that's like a lot of work. And if we do this, you're basically dividing the map into different levels, and then this is a course to find navigation. And in this way, it best strikes the balance between effectiveness and efficiency. And another thing I need to probably mention is that everything we talk about a vector database today is based on semantic matching. So basically, we need to find the chunk that is relevant, that is semantically similar to the input query. And sometimes we need a bit of both. So in the traditional database, we were using exact matches, exact string search to find relevant documents. And for vector database, we're using vectors and cosine similarity to measure the semantic to measure the semantically closest chunk to our input query. But in practice, we kind of need both. So what ends up happening is that we should run the exact match, grab the top 100 matches. We should also run the approximate nearest neighbor, return top 100 matches, and then grab that 200 matches and then feed all of them into large language model. So that way we can strike a balance between exact match and semantic match. Okay, so everything we talk about is about so everything we talk about so far is about context engineering. So basically we need to provide large language model with the correct data and the correct context so that it can actually answer questions correctly. So takeaway message is that large language models have limited knowledge, and how do we boost it? Well, we usually use vector database as an external memory for large language models. So right now, if you go to all of those major commercial generative AI, if you look at it, if you see it is saying is searching in memory, things like that, it is actually trying to access certain vector database. And we need to retrieve the relevant context before generating an answer, and this will give us a better response in actual documents. And so basically, it not only serves as a better QA system, it is also serving as a memory in all of these, in most of these coding agents. So whatever agent you're using, if you want your agent to be slightly smart, if you wanted to memorize what you told him 2 conversations ago, or you want to memorize your preferences, like what you usually do, what is the context of this project, they definitely need a vector database to act as the memory for large language model. Think we should do. Let me demonstrate it using an online playground. So I'm not going to bother using something much larger than this. So this is a small document, and looks like they have split this into 26 chunks. And note that they are also creating these chunks such that these chunks are overlapping. So if you got like disjoint chunks for these documents, then imagine if you have a sentence spamming from one chunk to the other chunk, right? If you have one sentence and you cut it right here, what happens is that if you want to answer questions about that sentence, and if you grab this chunk, you're not going to answer it correctly. If you grab this chunk, it's not going to answer correctly. You need to grab both chunks to answer this correctly. So what we should do instead is that we should allow certain overlap between these chunks so that sentences don't cut off between chunks. So if you got an overlap between those chunks, then the sentence can finish itself before being cut off. And we can actually, so these are all of the things that we can tune in the vector database. And so basically, it is cutting it into 26 chunks, and the average overlap is 47 characters. And then if you click vector embedding, it has already done it. And so this is, so right now, it uses like 384 dimensions. And here it prints out the most principal dimensions. So basically, obviously you cannot show 300 dimensions on two-dimensional space. What they do is that they use something called principal component analysis. They map that 300 dimensions into 2 dimensions so that you can see it clearly. And then this illustrates how close each chunk is to your question. So this is a document about retrieval augmented generation. And let me ask questions. So what is the RAG is like a too easy question. Let me ask it a slightly difficult question. So what database is behind retrieval augmented generation? Okay, so as you change your question, it will automatically fetch the most relevant chunks. And sometimes you can ask a question that is far away from every chunk. And in that case, so that also happens. So if in that case, even with the database, it still cannot give you a good answer. So that can definitely happen. That usually a well-tuned RAG can answer your questions correctly up until like 80-90%, like 80-90%. But the thing with AI system is that you can probably never expect it to work 100% correctly. So in practice, what we're going to do is that we need to grab different data sources and ask them to cross-validate. So we need to ask this on this AI, and then they have a different vector DB, and we can ask them to cross-validate so that we know whether they answer our question correctly. And let's see what they have generated. So this is the system message. It's saying that so this is the part of the context engineering we talked about. So when you want to do context engineering, you need to provide it with a system prompt as well as a user prompt. The system prompt is you're AI assistant. You need to follow these pieces to answer user's question. So let me modify the user's message. I think I have something else. So what is the database behind retrieval augmented generation? RAG. Change. And so if the context is this, and looks like the context, if the original document does not really store anything about vector database, then it can still hallucinate. So let me see if you can answer this question well. The database, you can see that it is now not able to answer questions correctly because what we have in mind is the vector database. And now it is saying that the database behind retrieval is a large-scale knowledge graph or corpus text, something like that. So basically, the takeaway message is that the large language model is as smart as when Sam Altman or Elon Musk created it, and it is as smart as the context we give it. So if it cannot get answers in both places, that it cannot get the answer from the whole internet, or it cannot get the answer from the context you provided, then it's not going to magically come up with the right answer for you. So these are the limitations of existing systems that still need improvement. And the good thing with coding agent and stuff like that is that the margin of error is actually pretty high. So like we humans, like software engineers, generally we don't have like a ground truth when it comes to which part of the code base you should look at. So even if the RAG is only giving us like 80–90% of accuracy, then in practice it still works pretty well because later on, because it has the memory, we still have the chance to give it more prompts to correct it. Okay, so that's a small demonstration of retrieval augmented generation. So we could ask slightly more complex questions. So the takeaway message is that we can use RAG, so we can use large language models to improve databases, and also we can use database to support large language models. And the latter case is more and more so because large language model is all about context engineering, and database people like us, we are great at providing such context. And let's bring back to PostgreSQL. So we talked so much about NoSQL databases as well as vector databases. And do you think PostgreSQL don't have a response to those? Well, PostgreSQL have been constantly evolving. Like, although it is an open source database, but people have been constantly improving PostgreSQL to the point where PostgreSQL has become very versatile, and it has a lot of extensions to support these NoSQL databases. And now it can even support vector database. So now, basically, I don't think you can try this in the VixDB because they have fixed the your PostgreSQL configuration for you. But if you're deploying on a server of your own or your local computer, you can try implement the PostgreSQL as a vector database using the pgvector extension. So with that extension, your document can serve as both as a relational database and also a vector database. So, so basically, the PostgreSQL can also, with the right extension, it can also support most of the NoSQL databases functionality, as well as the most recent vector database. So for the document database like JSONs and stuff like that, they all have extensions in PostgreSQL. So you don't have to worry about learning about a database that's going outdated, because PostgreSQL is constantly evolving, is constantly catching up with other databases, and in the meantime, it remains the go-to relational database management system for classic use cases. And let me see. So let me ask you a question. So PostgreSQL has this extension, pgvector, and but in practice, people still prefer to use the SQLite database as the vector database. Why do you think that's the case, based on your knowledge in PostgreSQL? So we've used PostgreSQL for so many weeks. So why do you think for vector databases like in a coding agent or in Cloud Code or OpenClaw, why don't they have like PostgreSQL running as the vector database to manage your memory? Well, the reason is that it's too expensive, because PostgreSQL you need to manage the server. You need to PostgreSQL is built for many people working on a database, trying to write the database simultaneously, and it's not a very lightweight database that we can deploy everywhere. So in practice, for vector database, what they usually do is that they use SQLite as the vector database, and PostgreSQL remains the best relational database system for concurrency control and many users. So because if you remember our workflow from week 1, whenever we want to use the PostgreSQL database, we need to connect to the server first. We need to start a server. We need to manage our instance of the database. And that just becomes unnecessary when we just want a small vector database that does not need to be updated all the time. Like, we basically insert more vectors into the database, and we don't really have a lot of need to update or delete. So that's why it is not used tremendously as the lightweight version. Okay, let me do a small quiz, and then we can wrap it up. And then in the next lecture on Thursday, we're going to review the exam structure, and we're going to have a revision of what we have learned. So basically, I'm going to give you more practices that kind of mimic the exam questions. So first question, what is the main difference between the traditional DB and the vector DB? So vector DB is faster, or vector DB search by similarity, not keyword. Vector DB only works with images. Traditional databases cannot store text. So which one is it? B. Yeah, exactly. So for anything that we test from this part of the course, it's going to be as easy like this. So basically, vector DB we're searching by semantics and similarity, not exact words. And the traditional database can still store text. Let me find another one. What is an embedding? Well, is a type of index, is a way of encrypting sensitive data, is a way of compressing files to save disk space, or is a numeric representation of data or text that captures its meaning. So we should pick C. So that's the definition of the embedding. Embedding is basically a vector, and in the context of vector database, an embedding is basically capturing the semantics of the sentence or the document. So if you have two pieces of text with very similar semantics, then the embeddings, they should have they have the same length, or they're far apart in the vector database, they store in the same row in the database, or they're close together in the vector space. See, exactly. So that is how it's constructed. So if you got two pieces of text, very similar meaning, then the construct is that their mapped embedding will be very close together in the vector space, and if you compute the cosine similarity, it will be closer to 1 than closer to 0. So cosine similarity, I think, is pretty straightforward. And you search a vector space with the query dog. I guess we should have more complex or meaningful queries. Which result would vector return that traditional would miss? So the exact word dog spelled differently, or pet animal, or companion animals, or images of dogs, or documents containing letter D. So So what are the matches where the traditional database should miss and the vector database can actually pick up? Yeah, exactly. So that's the point of vector database. It understands the meaning of the word so that we can find the most relevant chunk. So exact words of dog and containing D, this can be handled very efficiently and perfectly by traditional databases using pattern matching. But there's no way we can do something like that in traditional database because we need to understand the semantics of these words. So what does the cosine similarity measure? Well, they measure the similarity between two vectors. So basically two vectors, we can grab them to the 0, 0 point, and then we can basically, we're basically computing the angle between the vectors and how similar they are. So what is the challenge with certain meanings of high dimensional data? So do they take too much space, or is it because it's too slow? Vector database cannot handle more than 1,000 queries, and high dimensional vectors cannot store on disk. Yeah. So if you have like meanings of high dimensional vector, comparing that with each of them is going to be very slow for the obvious reasons. So that's why we settle for the approximate nearest neighborhood, and we talked about inverted index approach, and we talked about hierarchical navigational small world approach. So ANN starts for approximate nearest neighbor because it is too slow, so we cannot settle for the exact nearest neighbor. We need to settle for the approximate nearest neighbor, so we trade a little bit effectiveness or correctness for efficiency. So approximate nearest neighbor is what ANN stands for. So HNSW is popular indexing algorithm for vector database. So what's the key idea behind it? It stores all vectors in alphabetical order. No. It compares every vector against the other vector. No, that's the exact opposite of what it does. It splits data into exact two halves recursively. No, like we never do that. So what it does is that it builds a layered graph, and then we do coarse navigation at the top, and then in the end we do fine-grained search at the bottom layer. So basically what we expect from you is that you understand HNSW is one of the ways we do approximate nearest neighbor. So approximate nearest neighbor has two ways, inverted index approach as well as HNSW. So what does the RAG stands for? RAG stands for Rapid Aggregation, Random Access Graph, or Relational Graph Database. So what does RAG stand for? So RAG stands for Retrieval Augmented Generation, and the vector database responsible for retrieval part, large language model is responsible for generation part. Okay, so the last question. So what problem does RAG solve when using a large language model? So large language model too slow to generate text. That's not the issue. Large language model cannot answer questions written in English. Not issue. Large language models have knowledge cut off and have no access to private data, and RAG supplies the relevant documents at query time. And D, large language models answer questions about mathematics. Well, the obvious answer is C. So RAG is basically doing the work of context engineering. So general purpose large language models, they have knowledge cutoff and they don't have access to your private data. And if you want to answer questions about your document, you need to supply it to the large language models so that they can build a vector database on it and then they can search on it. Well, most likely, if your document is too small, they'll just read the whole thing. But if your document is like your PhD thesis and something like that, most likely they will build a vector DB on it. Okay, so the key takeaway is that we expect you to understand what is embedding, what is cosine similarity, and comparing them pairwise is going to be too inefficient, and that's why we resort to approximate nearest neighbors, HNSW and IWF. And basically, we expect you to understand that RAG combines the vector DB with large language models for grounded generation. Okay? Okay, that concludes our lecture today. And on Thursday, we're going to do a lot of revision so that we can better prepare you for this, the exam. Thanks so much. Thank you.
Are we responsible for this week's content and the final exam?
Pardon?
Are we responsible for today's content and the final exam?
It's not going to be heavily tested. I'm going to make an announcement explaining what expect. So it's going to be super easy for you.